This lecture will speak about charged black holes. While from the physical point of view, the black holes that appear as a result of gravitational collapses should be almost neutral, because the stellar matter is neutral, and even if they were not, by consumption of the nearby matter and by the electromagnetic attraction, the charge would lower over time. These black holes played a significant role in the understanding of the general relativity, as well as they play a significant role in the quantum gravity and string theory. So let us start with presenting the generalization of Schwarzschild solution to the presence of electromagnetic field. Okay, so let us consider gravity coupled to the electromagnetic field. The action is given by Ricci scalar minus the square of the gauge field strength. This gives us the equations of motion in the form of Einstein equation, where in the right-hand side we have the stress energy tensor for the gauge field. And the Maxwell equation. The F itself is a closed one form, so we naturally have Tf equals 0. And F is the exterior derivative of the gauge potential. Good. So the Reissner-Nördstrom solution, which was found soon after the Schwarzschild solution, is given by the following metric. The solution is manifestly spherically symmetric, and static. And the gauge field is given by A equals Q of R dt minus P cosine theta. Here, the function delta, so here the function delta is a quadratic polynomial. So delta equals to R minus 2mr plus e squared equals to since every quadratic polynomial can be decomposed in two roots. Good. So we are considering a generalized solution, which includes for although unphysical but still geometrically interesting magnetic charge, and the total charge is given by q squared plus p squared. So we have the solution given by three constants. So we have the solution given by three constants. So m, which is mass, Q the electric charge, and P the magnetic charge. So depending on the values of the parameters, we are in one of the three possible limits. So first of all, let us m be greater than e squared by the absolute value. Then we have a smooth black hole solutions which has two horizons, an outer horizon which we would call R plus for the big root, and R minus for the small root. So the first one is the most physically relevant situation, where the mass dominates over the electric charge. The second branch is where the electric or magnetic charge dominate over the mass, and we have a naked singularity because both of the roots are imaginary. So this is an unphysical situation. In the real gravitational collapses, the gravitational attraction of the matter would be overcome by the electric repulsion if the charge dominates over mass. So, and the final situation is where these two things are balanced. In this case, we'll have a smooth black hole with a single horizon, which comes from the two horizons merging into one. So this is a special kind of a black hole, and we'll call such black holes to be extremal. We believe that such black holes are unphysical as well. In fact, we don't know of any scenario how they can form as a result of a physical gravitational collapse. Nevertheless, such solutions usually possess interesting geometric properties and are widely studied in string theory and quantum gravity. So, we will discuss these solutions later in this lecture. So, as for the Schwarzschild black hole, we also have the uniqueness theorem within the spherically symmetric class. So, we can state that the unique spherically symmetric solution of the Einstein-Maxwell equations with non-constant area function R area radius function R is the Reissner-Nördstrom solution. So why do we have to assume that the area radius function is non-constant? Well, if it is, then there is another solution, which is a direct product of two-dimensional IDD theta space times a two-dimensional sphere. Such geometries, this geometry is known as Robertson-Bertozzi geometry, and in fact it has a direct relation to the extremal black hole case, and we will discuss it there. So let's discuss the case of a non-extremal black hole first. Our goal would be to draw the Penrose diagram, and we start by introducing the Eddington-Finkelstein coordinates and then the Kruskal-like chart. So if you recall, from the previous lectures, we first introduced the proper radius, and from which we find that the R star is R plus some constant times logarithm of R minus R minus over R minus plus logarithm R minus R plus R plus. So it's an exercise to find these constants. Again, we can introduce the outgoing and ingoing coordinates. Using the ingoing Eddington-Finkelstein coordinates, the metric is So, which geometric properties can we see? So, first of all, R equals 0 is again a Cauchy singularity. Secondly, we see that the horizons are indeed null hypersurfaces. Thirdly, and this is an exercise, is that similar to the Schwarzschild spacetime, we can show that the light cannot escape from behind the outer horizon. So we can show that no point in the region inside the black hole can send a signal to Scri plus. Finally, as for the Schwarzschild, we knew that radial null geodesic would reach singularity at a finite parameter. Here, similarly, they will reach R equals they will reach the inner horizon at the finite time. So radial null geodesic. Any horizon at a finite time. Good. Now, let us introduce Kruskal-like coordinates. So we will have to introduce two charts. The first chart would cover the exterior and the region between the two horizons. And the second one will cover the full interior of a black hole. So we have two charts. So let us introduce u plus minus equals e equals to plus or minus where a couple plus minus are constants. So let us consider the chart that covers the exterior first. So we then naturally have the geometry given by the metric and the function r can be found implicitly from which is well defined in this chart. So this chart naturally gives us the Kruskal-like diagram. So we naturally have this surface. So naturally the surfaces r equal constant are given by the following curves. And these lines are given by r equals r plus, r equals r plus. So naturally, we have the same regions as in Schwarzschild. First of all, we have two asymptotically flat regions, 1 and 4, and we have the black hole region 2, and its time reverse, the white hole region 3. Again, there is a bifurcation to sphere given by u plus equals v plus equals 0. Now, we want to construct a second chart and match them on the interlap. So, the interlap in the region 2, which is the region between the horizons. So, in the region 2, which is given by r minus r plus, follows that u plus v plus are greater than 0 and 0 and u minus v minus r less than 0. So in other words, in the minus chart, the region 2, that is the region between the two horizons, will be a white hole region in the Kruskal diagram. So, in the region that, so in the chart that covers the exterior of the black hole, we have the metric given by plus the two-sphere. So if you draw the Kruskal diagram, we will have region 2 here. We will have two new regions 5 and 6, and we will have a region we shall call the 3' region. So we naturally have the singularities. In the regions 5 and 6. In 5 and 6, and notice that the singularities this time are time-like. So finally, we have a new region 3'. Finally, we have a new region 3'. And one can show that the chart in the region 3' is diffeomorphic to the region 3. So again, this region is diffeomorphic to the white hole region as seen by the exterior of the spacetime. So this means that with respect to the 3', we can then define the new exterior and the second asymptotically flat region, and then the new black hole spacetime. And in general, this diagram can be continued on and on. So this allows to extend the Penrose diagram for the Reissner-Nördstrom black hole indefinitely. Let us draw how it looks like. Okay, so we start with the exterior region 1. We know the Kruskal diagram of this part because it is given by the exterior Kruskal-like chart, by the u plus v plus coordinates. So we have the black hole region, that is the region between the two horizons, r equals r plus and r equals r minus. We have the second asymptotically flat region, and we have the white hole. And we have the white hole. Now, let us see what happens with the interior Kruskal-like chart. Here, we have the region 2, and we have two regions that contain time-like singularities. The region 3' then allows to extend the Kruskal diagram indefinitely. So we'll have the region 3', we'll have the region 1', 4', 2', then 5' and 6', and so forth. So what about the asymptotics? Well, the future null infinity for the region 1 is given by this line. The past null infinity scry minus is here. Here we have the second set of the null infinities. And so on and so forth. And so on and so forth, because the chart keeps introducing new asymptotically flat ends, and therefore new null infinities. While this diagram is correct, most of it is unphysical. If you look closely at the regions 5 and 6, they contain time-like singularities, and time-like means that these singularities can be avoided, escaped. So if you look closer at, let's say, region 5, we may have a radial null geodesic escaping the singularity at some moment in time. So in particular, this means that this region is not predictable, and we in nature to have a Cauchy horizon in our scenario. So indeed, let us consider usual Cauchy surface given at some constant time t equals 0. Then the domain of the predictability for the Cauchy surface would be the rest of the region 4, the rest of the region 1, and the region 2 up to the horizons. Because we cannot extend, because by this nature that we can have radial null geodesics starting from the singularity, we cannot extend predictability behind r equals r minus. So in total, we have Cauchy horizons. So in total, we have Cauchy horizons we have Cauchy horizons in the future, and similarly we have Cauchy horizons in the past. So from this diagram, it follows that the only region that is worth taking seriously is the exterior Kruskal-like region. That is the regions 1, 2, 3, and 4. Now, we have Cauchy horizons, which is of course quite pathological, and it all looks like a serious violation of the strong cosmic censorship. Well, in fact it's not. We believe that such horizons are highly non-generic. And one of the reasons for such non-genericity is that these horizons are in fact unstable. They exhibit an infinite blue shift. Let us look closer. So let us consider the situation of an infalling matter. Let us consider two observers, A and B. The observer A crosses the horizon of a black hole and then goes along a following causal world line. The observer B stays outside, and let's say that it always stays at a constant radius. So this is observer B, and this is R equals constant line. So let the observer B keep sending light signals after some periods in time, and the signals go directly into the black hole, so along the radial null geodesics. So as you can recall, it will take observer A only a finite amount of time to reach the Cauchy horizon R equals R minus. At the same time, even if observer B keeps living for forever until it reaches the future time like infinity, and it keeps the procedure of sending the light signals directly into a black hole, the observer A would receive all of them. So naturally, it means that the physics is unstable, because if you have some small exterior perturbation that just keeps going over time, these perturbations would grow infinitely in the inner region. Basically, the signals would suffer an infinite blue shift, which would lead to a singularity there. So, in particular, in numerical simulations of such gravitational collapses, we have the singularity forming instead of an inner horizon. So, and this behavior is generic for the boundary data, well, for the boundary initial data. So, therefore, we believe that the picture we have just drawn with Cauchy horizons is extremely non-generic, and it's not a proper physical model. Now, let us consider the extremal case. The metric is then naturally, we can also introduce ingoing Eddington-Finkelstein coordinate. So we introduce V equals T minus R star, where the R star is given by R plus 2m logarithm minus m squared r minus m. Minus m. So the metric is then ts squared equals So in particular, we have analytically continued into the interior region for r less than m, which is a black hole region. Again, we have the curvature singularity at r equals 0, and r equals m is a null hypersurface. Let us draw the Penrose diagram. So we initially have the exterior block bounded by the two horizons, the future and past horizons. And this essentially is the singularity. So we have going here. Again, this can be infinitely continued as for the non-extremal case. And we will have an infinite chain of such asymptotically flat ends. So essentially we have only two regions here. We have the region 1, which is the interior, and the region 2, which is the, so we have the region 1, which is the exterior, and the region 2, which is the interior. And it also contains a timeless singularity. So by the arguments of the above, the event horizon H plus, as well as the past event horizon H minus, are the future and the past Cauchy horizons as well. Yeah, well, the geometry features future and past null infinities, as well as the special infinity and the future and past time-like infinities. So let us consider a typical Cauchy surface. So let this be theta, which is constant time slice sigma. So let's have sigma, which is constant time slice. Then a surprising feature of this geometry is that it is no longer the Einstein-Rosen bridge, as we saw in Kruskal and non-extremal Reissner-Nördstrom case. Instead, on the edge of it, we have a singularity. Effectively, the geometry is that of an infinite throat. So which doesn't end anywhere, unlike the usual Kruskal or non-extremal case. So what does this infinite root mean? So what does this infinite root mean? Well, let us consider the time necessary to. So what does this infinite root mean? So let us consider the time necessary for the ingoing observer to reach the horizon. So the proper length of time the proper length of time So what does this infinite root mean? Let us consider the proper length of line stretched from the point in the exterior to the horizon. So let the line start at some r0, which is greater than the horizon radius value. And then we naturally have that the length. Then we naturally have that the length of the line equals to the integral from r0 to m of the dr star equals to diverges. So the surface of constant t exhibits an infinite root at the horizon. So the geometries of such extremal black holes have a number of very nice features. So let us consider the near horizon limit of this geometry. So let us introduce the parameter lambda equals to r minus m. Then, to the leading order in lambda, the geometry is so we clearly see the ADS2 factor and the two-dimensional sphere. So this geometry, the leading order of the expansion at 0, which is known as Robertson-Bertozzi geometry, is the direct product. The second surprising feature is that this leading order in the expansions is actually the solution of Einstein equations itself. So So this is a general feature of extremal black holes. The geometries which are obtained by the near horizon limit, which is effectively the limit when we zoom in onto the horizon, are called near horizon geometries. These geometries are usually algebraically special, and studying and classifying them is important in string theory. So next time we will speak about rotating black holes.